Welcome to this afternoon session. It is my pleasure to introduce Augusto Gerolin. He will talk about synchron algorithm and application to generative models.
So thank you very much for the introduction. So thank you all the organizers for making this workshop in this very nice program. So I'm going to talk about the entropic-regularized optimal transport, which is also known in the literature as the Schrodinger bridge problem. So this is there is a very vast number of works in this field. So it's a very active field nowadays. So since we are at the field at the Simons Institute, I'm going to take the point of view of numerics, in particular, presenting a new variational strategy, a new variational proof for the synchron algorithm. So the motivation of my talk will be really introduce a new proof of the synchron algorithm that works in the multi-marginal setting. So before getting into the core of the talk, let me just give you some context. So like my starting point for this presentation is like the following problem. So it starts with rho 1 and rho 2 is the given data, two probability measures, one in a space X and another one in Y. And I want to minimize the Kullback-Leibler divergence between a transport plan gamma and a kernel given by the exponential of minus c divided by epsilon among all the transport plans. So all probability measures in the product space having the marginals equals to rho 1 and rho 2. So this problem has been exhaustively studied in different generality, including for more general kernels than the ones that I'm assuming here. But the nice feature about this kernel, when it's given by the exponential of minus c, is that this is equivalent to the entropic regularization of optimal transport, where the regularization is given by the channel entropy. So it's very well known under those generalities that like there exists a unique solution due to the strictly convexity of this problem. And this is given by this Gibbs energy, exponential of minus c, multiplied by two weights, A and B. And those weights are precisely the weights that make gamma having the correct marginals, rho 1 and rho 2. So for those familiar with optimal transport, so if I'm matching the red dots, so the distribution rho 1, with the blue dots, the distribution rho 2, when epsilon goes to 0, I have straight lines. As soon as epsilon increases, we move to a set where you have Brownian bridges instead of the displacement interpolation, the Macan displacement interpolation. So the effect of the regularization on the plans is very well known. So you want to make the plan a little bit more fat. So it's not singular with respect to the product measure rho 1 and rho 2, but become an absolute continuous measure with respect to rho 1 and rho 2. This is not restricted to the distance square cost. So the setting is quite general. It can accommodate, for example, Coulomb coasts that are important in quantum chemistry and density functional theory. So in all those different settings, we can show that not only there is the convergence of the energy, so the cost with epsilon converges as a number to the OT problem when epsilon goes to 0, but also you have the gamma convergence, so the convergence of the plans. For every sequence of minimizers, gamma epsilon, we have that this converges to the OT problem when epsilon goes to 0. So in like how to compute the optimal coupling gamma epsilon. So the way of doing this is passing by solving the Schrodinger system. So like the minimizer gamma epsilon has this form if and only if solve the Schrodinger system, the so-called Schrodinger system, which is basically applying the condition that the gamma belongs to pi of rho 1 and rho 2 to this specific shape of the minimizer. So in general, it's not possible to solve this system analytically unless in very special cases. So last year appeared a series of works where consider the case when you have the distance square and rho 1 and rho 2 are Gaussians. So in this case, you can solve explicitly this system. And the reason why is because when you have Gaussians, you can take A and B exponential of quadratic forms. So then you just need to optimize the coefficients of those forms and you can solve the system. But this is quite special. And in general, you need to compute using the synchron algorithm. And I say briefly what the synchron algorithm is. Just is the simplest algorithm that someone could introduce. So the idea of the synchron algorithm is that we initialize two vectors, A0 and B0, and we define the sequence AN and BN iteratively using this structure of the Schrodinger system. So I'm just dividing the integral, passing to the other side, and this gives me an iterative way to define the sequence BN and AN. So at every iteration, the idea is that I'm getting closer to the A and B that is the solution of the Schrodinger system. So this has been exhaustively studied. Like I guess many of the people who have worked in this problem is or online or in this audience. So there is different proofs for convergence of the synchron algorithm, and also approximates like the distance linear in time. So just to make a parallel and try to explain a little bit of the difficulty that we faced. So one approach that was introduced by Synchron, Franklin Lawrence, and also by Chain, Georgiou, and Pavon. So I'm very happy to show this in front of you, no? Right? So the idea is that we can show that like those synchronous iterates are like a contraction under the Hilbert metric of the projective cone. So the idea is that you consider a cone of, let's say, pi rho 2, which are all the sets of transport plans have one marginals equal to rho 2, and another set where we have all marginals equal to the other. And basically, you can define a metric on this cone that, roughly speaking, is the angle. And basically, you can show that like every iterations, you are fixing one of the marginal, and this is a contraction. So when the number of iterates goes to infinity, we are converging to the correct one, where you have A epsilon in the right coast. So the nice feature of this proof that like you not only give the convergence, but gives to you automatically the rate of convergence of the plan. We get interested on this problem because we want to understand the synchron algorithm, where instead of having two marginals, you have finitely many. So instead of having a system of two equations, you could have a finite many equations. And we didn't find a way of proving the convergence of synchron, trying to adapt these ideas of the Hilbert metric, showing that the synchron iterates are contracted in the Hilbert metric because you needed to deal with finite many angles. So then we developed a different strategy. So before going directly to the talk, just want to mention some reference, because this is a very wide topic. I'm going very focalizing in one aspect of it. So I recommended 3 surveys. So one of Martin Indel, from more the numerics and the matrix viewpoint, and 2 beautiful surveys, like with more probabilistic, large deviations and control aspects done by Leonard, Chain, Georgiou, and Pavon. Very recently, one of those. So the plan of the talk is the following. So I try to introduce a duality approach for the entropic-regularized optimal transport. And the ideas of those duality approach is going to give us a variational proof for the convergence of the synchron algorithm. Although I'm motivated by the multi-marginal case, you see that like there is not much difference on doing this in 2 or many marginals. I'm going to fix in the 2 marginal case because the notation is much simpler. And if I have some time, I'm going to also try to present some insights into generative models. So what is the idea? So let's fix it, the setting. So I have like rho 1 and rho 2, 2 probability measures on 2 Polish spaces, X and Y. The cost function, I'm assuming that is bounded. We can also do a similar analysis when the cost is Lipschitz, but it's better to keep more general. And epsilon is a positive number. So we can define the dual functional, which is very similar to the classical Kantorovich formulation of optimal transport, with the difference that instead of the constraint, we have a penalization given by the exponential of u plus v minus c divided by epsilon. In the Kantorovich problem, I'm trying to maximize the dual problem, assuming that u and v are like in natural spaces. So the LX exp are like really the natural X space that we should consider, such that the dual functional has a finite value. So one important remark is that the dual functional for the numerical viewpoint has many advantages because this is an unconstrained functional. So this is the Cantor-Ovchi problem in the regularized case is unconstrained. So this has been exploited a lot numerically, the advantage of it. But analytically, it's not so obvious how to get compactness for this problem. So just to make a parallel, so if you look to the classical OT problem, as soon as we assume some boundness or some regularity on the coast C, automatically you get also some regularity for the potentials U and V that you can use to get compactness of the maximizing sequence. No? In particular, we can define the C transform. So we can define like the C transform of U by the inf of Cxy minus U of X. And automatically, if C is Lipschitz, we get automatically that UC is Lipschitz. And you can also have that we just needed to do this. So here with this functional, because we don't have the constraint, is not that obvious, but there is a equivalent object that does the job. And the object is the entropic transform or the C epsilon transform that is defined like the log sum exp of those potentials. And this is really the right object that allow us to get some regularity on the potentials to get compactness of the maximizing sequence. So in particular, properties of the coast function. So for example, if it's Lipschitz or omega continuous, translate into the properties of the potentials. Another property that is important for the convergence is that if C is bounded, the C epsilon transform or this entropic transform is a one Lipschitz compact operator between L infinity and LP. And of course, you have also like geometric properties, C is concave with respect to a variable. Also, the potential is going to be. So, and this is very consistent to the classical case when you have epsilon equals to 0, because like by the Laplace principle, when you send epsilon to 0, you recover here the C transform. So you can really see this as a regularization of the C transform. So, and with this in hand, with this in mind, so we can show that like the supremum of the dual problem is reached by a unique couple U0, V0. Of course, we have some symmetry of the dual. You can add and subtract a constant, and this does not change the value of the coast. So like you can show that there is 1 up to trivial transformations. And in particular, both are L infinity because we assume that the coast is bounded. This symmetry is something that plays a role to make the problem a little bit more difficult. But like we can use the C transforms to deal with this symmetry. So like we can show that there exist two potentials, U star, V star, that are bounded. And in particular, there exists a constant that one potential is the C transform of the other. So you can get rid with this symmetry, playing a little bit more with the C epsilon transform. With all of this, like to show the existence of the maximizer is basically apply the direct method of the calculus of variations. So we pick two maximizing sequence, apply the C epsilon transforms to get the boundness of the potentials via the lemma. Then by Banach-Kellogg rule, we get convergent subsequence. And then the existence of the maximizer follows by the upper semi-continuity of the dual functional. So it's really like a very classical calculus of variations approach to the existence of the maximizer. Okay, so that is the idea. To summarize, what we can get is like all the following are equivalent. So there exist the two maximizers of the dual problem. One is the C epsilon transform of the other. If you plug U and V, if you take exponential of U and exponential of V, the following gamma solve the Schrodinger system. So they have the correct marginals. And in particular, it solves the Schrodinger system because the unique one will have this form. And you have like the primal dual condition. So like the primal problem coincides with the dual problem. And one remark is that in some applications could be natural, instead of using the regularization like has a reference measure ρ1 tensor ρ2, it could be natural, for example, to use a reference measure in a manifold. So you could, instead of using the regularization of the entropy with respect to ρ1 and ρ2 with a general reference measure, this does not play any game in our analysis, because one problem is basically up to a constant, they have the same value. And to do the existence of the potentials, you just need to work with the correct potentials by shifting by minus epsilon log the density. So all the analysis that we are doing here works regardless of the reference measure that we choose. So it's going to change a little bit the definition of the C transform, but like the proof goes in the same way. So the reference measure does not play an important role. And also, everything, since everything is variational, all the previous analysis can be extended to the multi-marginal case. So if you have two or finitely many works, it's going to work in the same way. So why we are interested, just one slide to try to say that this is useful. So like in the multi-marginal final transport, like has been appearing in different contexts. So has like the time discretization of Euler equations, has Wasserstein barycenters. Also in quantum chemistry, in density functional theory, like optimal transport with Coulomb coasts become very important. Very recently, on also connections between multi-marginal optimal transport and probabilistic graphical models, and in mathematical economics, like matching for things. So the structure of the problem is the same. Instead of have two, you have finitely many, but the notations become a little bit heavy. So previous to us, there was a very nice article by Carlier and Laborde that showed existence uniqueness and smooth dependence with respect to ρ of the multi-marginal Schrodinger system, assuming that the data are in L infinity. So which is a little bit orthogonal of what we did. So now let me go to the proof of convergence of the Synchron algorithm. So I mention again, like how is the Schrodinger system? So we initialize two sequences A0 and B0, and they define Bn, An in the following way. And the theorem, which is in the two marginal cases, is very well known to works. Like if you pick the EFFP or Synchron sequence, then there exists a constant, a sequence of constants like lambda n, such that An converges in NP to A, Bn converges in NP in LP to B, for NP, where A and B solve the Schrodinger system. And in particular, we not only get the convergence of the potentials, but we also get the convergence of the planes. So, and what is the idea? The idea to prove this is very similar to the analysis of the dual. The only remark that we need to make is that if we do a change of variable, instead of looking in terms of An and Bn, we want to look in terms of potentials Un and Vn. So if you do this change of variable in the Schrodinger system, let's say for the first one, then by applying the log in both sides, we get basically that Vn is minus exponential the log of the integral in x of E of Un minus 1 of x minus C of x and y integrated in ρ1 of x. So I'm integrating ρ1 of x, so this gives me a function of y. And this is precisely the Un minus 1 C epsilon transform. So basically what we are doing when you are computing the Synchron iterates, you are basically doing a C epsilon transform. So, and as you know, this C epsilon transform gives me a increasing sequence in the dual problem. So the idea goes very similar to the proof of existence of potentials, because like by applying the C transform, you get some regularity on the Synchron sequences. So we can show that there exists a constant such that Un minus ln, Vn plus ln are bounded. That sequence Un Vn increases and is bounded by the primal problem. And thanks to the property that the C epsilon transform is a one Lipschitz compact operator, you get also that those sequences are pre-compact in LP. So the only work to do now is to compute the limit between the V epsilon transform and V, the same for U, to get the convergence. Because if you know that one is the C epsilon transform of the other, they are the maximizers of the dual potential, the dual problem. So getting the convergence of the UN, V, and LP is easy to translate this to the convergence of the plans. So it's a completely variational problem, variational proof of the Sinkhorn algorithm. And again, the previous strategy is not limited for n equals 2, but you can use finitely many. There was a work of Carlson and Ring in 2017 that used a similar strategy in the discrete case to prove the convergence of the multi-marginal Sinkhorn algorithm. So all our work, you can see, has an extension of this work when you have continuous probability measures. And very recently, like a couple of months ago, Carlier, using this methodology, also get the rate of convergence. So like the disadvantage of this method, since it's purely variational, we get the convergence, but we don't know the rate, which is different when you use the contraction on the Hilbert metric that is for free. But like doing some work, we can also get the linear rate of convergence of this problem. So just a remark, I guess it's going as expected. So this can be generalized for more general entropies. So like, imagine now that you wanna do a regularized optimal transport problem, but instead of choosing the Shannon entropy, you wanna choose a general entropy. So, and by a general entropy, I consider a convex, lower semi-continuous function that is superlinear at infinity. I assume that like it behaves well, like it's 0 in 1 in the derivative of 1, but this is just for simplicity. This is not a restrictive condition. And you want to define the similar problem. So the motivation of using different regularizations comes from the sparsity of the plan. For example, you can see in the quadratic case that even epsilon is very big, you still get a solution that is very sparse. This has been studied previously, of course, for the Shannon entropy, for the Tsales entropy in the context of ecological inference, and in the quadratic case by many authors. And the general case has been looked at very recently, so in the discrete case in 2018, and then in 2019, 2020, in the continuous case, but the settings were a little bit different. So the difference between our work and the work of Lawrence and Mahler is that in our work, you can see that we really consider gamma has absolutely continuous with respect to the product measure, while in their work, the work of Lawrence, gamma is absolutely continuous with a reference measure. And unfortunately, in the general case where you have a convex entropies, those are not equivalent. And in our case, it's easier because since we are regularizing with respect to the product measure, we can get similar regularity of the potentials, which is not true in their case. So very, very recently, so other authors consider a similar problem. So this year, Terher and Gonzalez Sanchez relaxed the hypothesis of superlinear at infinity. So considering like more general F divergence regularizations. And last week, like X and Marcel Nutz did some quantitative stability of this problem as well, and can also deal with the distance square case in two marginal, so with the distance. No? So in what we can get here is very similar. So the prime and dual problem coincides, and moreover, you have an optimizer, a unique optimizer for the problem, gamma epsilon, which has a very similar shape. So phi star is the convex conjugate of psi, of phi, sorry, phi star is the conjugate of phi. So the plan has like the derivative of the convex conjugate, and here you have the two Kantorovich potentials minus c divided by epsilon. So the strategy is very similar, but we can look a little bit more abstract. What are the entropy transform when you have a general entropy? So the idea is that we define, so here should be a belongs, right? So here we define the entropy transform by taking the argmax of the dual potential with respect to one variable. which you can show that is equivalent to solve this problem, which is very nice, that gives a very nice implicit equation that is precisely the generalization of the Schrodinger system when you have a general entropy. So if you have the similar equation with ρ2, where we maximizing V, we would have precisely the Schrodinger system with a general entropy. And thanks to this, we can get a similar structure. So assuming some regularity on C, this also translates to the C epsilon transform of the potentials. So in particular, if C is bounded, if C is Lipschitz, we get the same for the potentials, and it's also a one Lipschitz compact operator. So, and then having all of these in hands, we can now look at the Sinkhorn algorithm in a different way and define the phi Sinkhorn algorithm for a general entropy by basically the alternating maximization of the dual problem, where I just maximize with respect to U, keep the V fixed, and the second iteration, I maximize with V, keeping U fixed. And this gives me like the similar updates. So I initialize U0, V0, and compute the next U by solving implicitly this equation, and compute V by solving implicitly this equation. So in the proof of convergence goes in the same way. We need like the compactness of the entropy transform, plus the fact that like all the time that I apply the entropy transform, I'm increasing on the dual functional. So I'm getting a higher value of the dual functional that is bounded by the primal problem. So just a last remark, we can also get also in the convex regularizer, the Frechet differential of the OT problem. So here there is a typo. Here should be phi star, so the convex conjugate of phi. So what you get that like in both sequences are weakly converging, so the OT problem is continuous, the convex regularized OT problem is continuous, and also like the gradient is well defined, where like the gradient you can compute in terms of the optimal potentials U and V. So just to mention briefly how this can be used to understand some problems on generative models. I know that Duo is going to talk more about this later, so I'm just going to mention briefly. So Wasserstein becomes very popular in the context of generative adversarial networks because of the power of generate realistic images. So those images that are generated here are of people that does not exist, but that was learning from a data set of celebrities. So this was done by people from NVIDIA, so in Aalto and Helsinki University. So and there was a very important threshold of the use of Wasserstein distance in this context. So like very briefly speaking, because I know that there are at least 2 talks about the subject on this workshop. So the idea of GANs that you have a generator and a discriminator. So the generator starts with purely random noise and try to challenge the discriminator to distinguish what is a real or a fake image comparing to the training set. And the discriminator acts as a guy who needs to be able to distinguish between what is a real image that came from the data set or what is a fake image that the generator is producing. So the main idea of the Wasserstein GAN, so the paper of 2017, was to replace the original setup of Young-Goodfellow that used the Shannon, Jensen-Shannon divergence for the discriminator, to replace this discrimination for the dual formulation of the one Wasserstein distance, this one. So, and after that, there was a paper that is called WGAN-GP, so the gradient penalty, that improve a little bit the training. So, and very roughly speaking, so the idea is like to solve the dual of the one Wasserstein distance using neural networks. So basically, we exploit a very nice property of the one Wasserstein distance, that the C transform of one potential is basically minus the potential itself. So, and then the dual conditions here, so the constraint you can really write has like 1 of x minus 1 of y smaller than the distance cost. And this is basically saying that like your potential is like 1 Lipschitz. So it's Lipschitz with a constant 1. So the biggest problem is really like to enforce this Lipschitz constraint when we parameterize using neural networks. So in the paper WGAN GP, so gradient penalty, they reinforce this Lipschitz constraint by penalizing the gradient of the Kantorovich potential, doing this soft regularization here. And this was very impressive because you really were able to this worked very well when you are doing tasks like density estimation generation. But what was very surprising to me is that when you do this gradient penalty, you are actually not learning the Kantorovich potentials. So in the sense that, so we did a comparison which like the true W1 distance computing on the midi batches is given by those black dots that is here. So and when you compute this using a C-transform approach, what you would do in general when you compute exactly, so you really see that like the C-transform approach coincides with the true Wasserstein distance. So the C-transform approach using neural networks. While if you use this gradient penalty, you have like a huge difference between what is the true value of the Wasserstein distance and the potential that is learned by the gradient penalty method. So the same happens when you use the C epsilon transform and then entropic regularization. So and we understood that like the Wasserstein approach are not really learning the optimal potential in the sense of optimal, like the one that solves the optimal transport problem, but getting a suboptimal solution that works very well. So we also made some experiments to see the stability. So like the C epsilon transform, where I use epsilon equals to 1, is very stable when we compute on mini batches. So like the red is like the one that we compute using neural networks, and the blue is the one that we compute exactly the Wasserstein distance. So we take a very small number of mini batches, so we can compute this with reasonably fast using an exact solver. While if you see the gradient penalty, there is an enormous discrepancy, and it's very stable when you compare with the true one. And what is very surprising for us is that despite the fact you are not learning the optimal potential, so you are not learning the real Kantorovich potential, when you are talking about generation tasks, the gradient penalty and the weight clipping do much better than the C epsilon transform, although we learned the better potentials. So the C epsilon transform and the C transform, so you converge to a sort of k-means of images, while with few iterations with the gradient penalty, you converge to things that looks like a face. And this was very surprising to us. So we look a little bit in the literature together with an excellent master student like Lorian Kotolf that is at the University of Amsterdam. So he went well a little bit on the literature and did some experiments by himself. So he managed to deal with the small data sets using the entropic regularization and like a C epsilon approach on mini batches. So if you have like low dimensional sets like Gaussians, like mixed Gaussians, he's able to learn very well with like different values of epsilon, not too big. Not too big means epsilon 40. Also with demi-ningst, work very well. Of course, when epsilon increases, you get some bias. But again, when you get a database that is too big, big means between m-ningst and celebrity A, this does not work very well. This epsilon approach learn better the potentials, so are closer to what would be the true entropy Kantorovich potential, but are very far away of being good enough to generate images. And there are very nice theoretical and experimental insights. So one was by Jolicoeur-Martineau, that she conjectured that the weakness of the divergence or the weakness of the distance, so it's not really a good indicator for sample generation. So we like a lot the idea that using the Wasserstein may improve the GAN training, but this may be not true. So the weakness of the divergence don't play an important role. And actually what I learned from Lorian that is like hyperparameter highly affects the performance of the Jensen Shannon gun. So if you are very good on dealing with neural networks to find very good architectures, you can get very realistic images, even using the Jensen Shannon divergence. And what seems to play a very important role in this context, this was a finding by Jan, that is a PhD student of Carola, that it seems that like enforcing the one Lipschitz constraint seems to play a role that's much more important than really finding a nice way of learning the optimal potential, to find really the maximizer of the optimal potential. So there are experiments where you regularize with a Lipschitz regularization the Jensen-Shannon entropy that works as good as the WGP, or very close to the WGP, even if there is no theory that justifies to use this regularization. And also, like there is also the curse of dimensionality of the Wasserstein distance. So that seems that like you learn when you are doing mini batch a false global optima, in the sense that like the kind of minimum that you learn when you are doing a sample estimate of the Wasserstein distance is different from the global minimum. And I like a lot this paper that they summarize those ideas in a very nice way, in a very beautiful way, that retains in the mind that is like Wasserstein gun works because they fail to approximate the Wasserstein distance. And I guess this is a very nice message that's saying that you don't need to learn the optimal potentials to be able to do very good generation tasks. So when I don't know, I may stop here. So thank you very much.
Thank you.
Thank you.
Any question?
Thank you so much. So the C-epsilon transform involves an integral, which is high dimensional, I guess, if you have high dimensional data. How do you do that numerically?
Monte Carlo. So you just approximate with Monte Carlo. It's true that it's high dimensional, but since you are solving this using backpropagation, so you just need batches of size, I don't know, 64 or 228. So this is doable with Monte Carlo. And in theory, the error is very small.
Thank you.
On the mini batches, of course. If you go to celebrity, the error may be huge. But very nice question.
Okay, let's try.
I can listen to you.
Oh, yeah, I don't understand. So maybe. Very nice talk. I have a question regarding what's the phi channel?
Okay, very nice.
But computationally, how do you realize?
No, this can be very bad because we don't have the additivity property of the exponential, which is very handy to write explicitly the iterations. So one way, very stupid, to do this is really to do gradient ascent in one of the variables. So one way of doing this is really like thinking Sinkhorn has an alternate maximization of the dual problem. The dual problem with convex regularization is unconstrained. So you can really do this like using, I don't know, stochastic gradient ascent in each one of the variables, for example. Or you can really solve this guy using some Newton's method. Like those are the two ways that I would approach numerically this problem. The nice thing that we know that those two ways are equivalent, so you're going to go to the same solution. But I agree. Like I don't know, I'm not very good in programming, so I think like we needed to think a very clever way of using this more efficiently. For a while, it's a very nice algorithm that works on the blackboard, but for a general phi, it can be it's much more expensive than the classical Sinkhorn. So if you have the quadratic, it's not that bad. It's very fast as well. Now that I'm saying about this, during the bootcamp, Marco Couturi present a way of solving Sinkhorn using like automatic differentiation or implicit differentiation. And one question that I asked to him is, it's like he present everything using the Shannon entropy. But actually, the way that he compute the solution does not matter. the regularization that you have. So you could also use like implicit differentiation, and it's going to work in the same way. So I would say if you want to compute this efficiently, more in that direction than using classical ideas of Synchron. Yes.
We were talking about all observations, relative performance of different hyperparameter selection. So what do you mean by saying that one GAN does better than the other?
No, I mean, so it's really like the I metric. So there are two ways that I can say, no, one GANs do better than the other if in the I metric, I generate better images than the others. And here, I don't know, like I would be very happy that my GAN would work, but I cannot say that. So it's much worse on the generation task. Here you get to realistic images, here not. Another way of saying that is better or not better is like which one are computing more accurately Cantor-Ovde potentials. Because like you could completely forget GANs and say, I want to find a way of computing using neural networks the vastest-time metric, a way of estimating the vastest-time metric using neural networks. So in that sense, I would say that the C epsilon transform do better than the gradient penalty or the weight clipping because their estimates on mini batches are closer to in the C epsilon transform case and not in the gradient penalty. So I say that like on the if you are interested in generate nice images, we do worst. If you are interested in estimate the vastest metric, we do better.
Obviously, one thing the GAN is supposed to do is it's supposed to produce pretty looking images. Right? Another thing it's supposed to actually give you something that looks like a sample from the distribution of interest. Right? So, I mean, something that GAN could do is it could just memorize one real image of a face and just give you 1,000 copies of them, and that would pass the eye test with flying colors. Right? But then there's to be some additional, like there should be some technical way to check whether the batch actually looks like a reasonable batch sample. Right? So is that the second?
No, this is not something that we look at. Really, we did a very naive approach of look for the image and pick one that you find that is which one you would buy. But like the question that we are more interested in, it was like how well we can estimate the vastness distance, because like it's a problem itself, like how to compute it in higher dimensional data sets. And I would say that like the C epsilon transport approach works better in that sense.
And then just briefly, the very last comment to the very last slide. I think this is very interesting. So there's some work by Xin Yao and his collaborators on looking at the regularity of Monte-Carlo equation and how that fits into some of the stuff in the GAN literature. So in particular, if you think that the distribution of like the support of the face manifold or whatever is going to be some non-convex thing in the space of all images, but the regularity of Monte-Carlo tells you that if you actually learned the OT map, then you would the support of the push forward measure has to be convex. Also, so this is sort of another point in favor of this last comment that if you actually learned the OT map successfully, then you would only get one mode of the distribution.
You should send me this. I don't know, but just one thing that is important. I want to make publicity because I really like this article of that says really the WGAN don't work because they fail. But I know that he's going to speak this week, so that's why I mentioned very briefly.
Okay, one last question. The question was about
so the question was just on the gradient penalty. So in the gradient penalty, so why is that enforcing right like gradient u equals 1 everywhere and not gradient u less or equal than 1 everywhere?
That is a good point.
So did someone try also the inequality? Because maybe it plays a role, right? So it's, I don't know. So from the point of view of the results, then.
Good point. No, we didn't. At least I don't know. Like
0.
Yeah, but when you do on mini batches, right?
The square. the square should be outside of the max.
It's outside of the max. So we need to do something.
Yes, because otherwise the max doesn't do it.
Yeah, 45. Yes, 45.
But it's true, it's a very rough approximation. That is a miracle that works very well.
So I think we should stop here to get ready for the next talk. Thank you again.
Thank you very much.